Okay, so in today's class, we will talk about some basic elements of modeling, and this is not something which is very new. You might have learned some of these concepts in your basic course on networks and circuits, something coming from mechanics, or even as early as your high school physics. And we will see how all these basic elements which we will define can be used to model physical systems, and we will also find out if there is any analogy between different kinds of subsystems. Okay. So, we start by classifying things into several types. It could either be a electrical system, a mechanical, electronic, hydraulic, thermal and several other systems. And each of these models, as we will see, or each of these systems can be modeled in terms of certain very basic elements, right. And then we will see if there is any analogy between cross domain between electrical and mechanical systems. And through this lecture we will concentrate mainly on electrical and mechanical systems. Okay. So, in electrical systems, based on the type of source, we could classify systems either as being voltage controlled or current controlled source systems. Okay. So, if I talk of a voltage controlled system or a circuit, my basic system variables are the voltage and the charge. We will see why this is true, why it is the voltage and the charge, why not voltage and directly the current, or why not something else. And of course, the three basic elements which we all know from circuits are a resistor, inductor and a capacitor, and throughout this class we will restrict ourselves to linear elements. Similarly, for a current sourced circuit or a system, my basic building blocks or the basic system variable are the system current and the corresponding flux. I will also show you why this is true. Of course, the basic elements then remain the same, the resistor, inductor and capacitor. Okay, so how are these things defined? Well, we all know what a resistor is. It is an element which resists the flow of current in a system, and we all know this Ohm's law, V equal to IR models a simple linear resistor. If I go to an inductor, I know that the voltage across an inductor is given by d phi by dt, or in the case when the flux is linearly related to the current, we will have V equal to L di by dt. So, if I just write down some basic laws which we learn in electromagnetics, so phi is proportional to the amount of current, and in the linear case phi equal to L times I, where L is the inductance, and then you have this linear relation between, or this relation V equal to L di by dt describing a linear inductor. Similarly, for the capacitance, I know that the charge, similarly for the capacitance, we know that the charge is proportional to the amount of voltage, and in case of linear elements, Q would be C times V, and I have a relation that the current, which is nothing but the rate of charge, is simply C dV by dt. Okay. So, what we will concentrate now is on these two things highlighted in the blue. How do we apply relevant physical laws and get some final form of the mathematical model? Okay. So, again, coming from basic circuits, we all know what are the nodal and the loop analysis, and these are essentially coming from the part 6, right. So, whenever we do nodal and the loop analysis, we apply in the context of circuit either the Kirchhoff's voltage laws or the current laws and so on. So, once we identify basic elements, we interconnect them in a certain way which defines the circuit, and then we write down the relevant equations. Okay. So, the nodal analysis, as we know, is based on the current laws, and the loop or the mesh analysis we write down the voltage laws. And this is again not very alien to us, that the Kirchhoff current law says that at any node the directed sum of currents flowing out of that node is equal to 0. Similarly, the sum of voltages across closed loop is always 0. That is what the Kirchhoff's voltage law tells us, right. So, if I just very simply look at this little circuit kind of thing here, I would know that I1 plus I2 plus I3 is 0, and if I just look at this as a loop, I can say that V1 plus V2 equal to 0. So, just look at the sign sides here, I go from a plus to a minus, plus V2 is equal to 0, or in other words V1 is just minus V2. Okay, so let's start with a simple example. Again, we start with very basic examples which we already know, and then try to build upon those things. So I have a current source, a resistor, inductor, capacitor, all linear elements. And if I apply the Kirchhoff's current law at node 1, well, the circuit is a single node, that the input current, which is I, is equal to the current which goes through the resistor, through the inductor, and through the capacitor. Okay. So, what is I through the resistor given V? That is simply, I can write it as V over R. Across the inductor, it will just be 1 over L integral V dt. It just all these equations again come from the basic laws which we had written earlier, right? V equal to L di by dt. I can rewrite this as that the current is equal to 1 over L integral V dt. So, we had earlier that V is L di by dt, or di by dt is V over L, and I simply becomes 1 over L V dt. So, just rewriting things which we already know. And finally, the current across or current through the capacitor is C dV by dt. Okay, what else do I know? I already know that V is simply d phi by dt, which means the current now can be written as C d square phi by dt square, this term, and across the across the resistor I have V over R. What is V? V is d phi by dt. So, I have 1 over R d phi by dt, and across the inductor that will simply be phi over L, right. And therefore, in the earlier slide when I said, okay, let us just revisit that slide for a while, that the basic system elements are the current and the flux. This is what I mean. So, I have current here and the flux, okay, and of course, these are the basic elements which build my circuit, the capacitor, the inductor here and the resistance here, right. Okay. Now, if I do a loop or a mesh analysis, it is also called something like a series RLC circuit with a voltage source. Again, all elements are linear. I have a voltage source V. Then, if I just apply my voltage laws, that the total voltage V would be the voltage across the resistor plus the voltage across the inductor plus the voltage across the capacitor, with the current flowing in this direction. Okay. Again, I know these things again, that V, the voltage across a resistor given I is simply I times R, and V across an inductor I already know from my previous slide that V is L di by dt, and voltage across the capacitor can be written in terms of this 1 over C integral I dt, in the similar way as we had written the current expression for an inductor. Okay. So, where does this current come from? Well, current is simply the rate of charge, or I equal to dq by dt, which means that V can be written as L d2I by dt square. Just put this guy over here, I is dq by dt. So, you will have a d2q by dt square, R times I. So, again I is dq by dt. So, I have R times dq by dt plus q over C. Again here the basic things are the voltage and the charge. Okay, we will quickly go back and check if it is true or not. So, when I said that for the voltage sourced system or a circuit, the basic system variables that define my dynamics or the equations are the voltage and the charge, right. And we were somewhere in this step. So, we applied relevant physical laws and got some final mathematical model. We will see again verify that. We started with the basic physical model, writing down the basic conservation laws to arrive at this dynamics of the system. Similarly, over here, a voltage controlled circuit or a voltage source circuit, I start with my basic laws and I arrive at this differential equation, which is the mathematical model of the system. Okay. Now, I go to mechanical systems. This is something which we learn much earlier than we do electrical circuits, right, when we do things in high school physics. So, I classify motions either translational motion or a linear motion as I call, or a rotational system or something which has an angular motion about a fixed axis. Okay. So, what are the basic things here? If I talk of translational motion, my basic system variables would be a force which causes a certain displacement. In the rotational motion or the angular motion, I have a torque which produces some kind of an angular displacement. What are the basic building elements? I will have a mass, which is essentially like a kinetic energy element. I have a spring, which is essentially like a potential energy element, and damper, which represents the losses or friction in the system. Or it could also be like as we will see, we can also have an external damper to the system. Rotational motion, I would have the moment of inertia, I will have the torsional spring, and again the corresponding damping or the resistance element in rotational motion. Okay, so what is mass? So mass is a property of an element which stores kinetic energy, right? And what does this mass do? So when a force is acting on a body of mass m, it causes a certain displacement x. And what does Newton's second law tell me? That the force is just the rate of change of momentum, right? That's a statement of the second law. F is dp by dt, and if I use the relation between momentum and velocity, so momentum is related to velocity as p is mass times the velocity, where velocity, if I could write in terms of displacement, I will have dx over dt, and then I will have this final relation that F equal to mx double dot, or usually called as, also referred to as force, is m times a, or mass times the acceleration. Similarly, in case of the rotational motion, I have the moment of inertia, the property of an element that stores kinetic energy in the rotational motion, in such a way that when a torque is acting on a body of inertia j causing a displacement theta, then torque is j times theta double dot, with the same analogy over here. This is a direct one-to-one relationship between F equal to mx double dot and T equal to j times theta double dot. Okay, so the second element is the damper. Well, what is this guy? The damper is an element which is essentially which generates a force acting opposite to the direction of motion, right? It essentially blocks your motion or resists the motion. What are the examples? A natural friction which happens when we walk or when we drive a car, or dashpot. So these are the two examples, and how are they modeled? So if I have a force again causing a certain displacement x, the damper is modeled as F is b, which is a constant, which is like the damping coefficient, dx by dt, a linear relationship between force and velocity. Similarly, in the rotational motion, I have the rotational damper or the friction as a linear relationship between the torque and angular velocity, which is theta dot, written as T equal to T d times theta dot. Okay, the linear spring. As said earlier, linear spring is an element that stores potential energy in a way that when you have a force causing a certain displacement, then the spring, as we know, will have a restoring force which will act on the opposite direction. So if this is my force here F, and so this is the thing where the spring, and then the force of the spring would be somewhere here, I will call it Fs, right, in such a way that F. So if I write down the conservation of the force here, the sum of all the forces is 0, I will have F plus Fs equal to 0, and what we learn in school is we model this Fs as minus k times x, right, and then I put this here to I substitute Fx Fs equal to 0, resulting then in this equation, right. Okay, similar thing happens in the rotational domain also, right, that the torsional spring is a property of an element, it shows potential energy in the rotational motion. Similarly, when I have a torque that causes an angular displacement theta, then the torque and theta are related linearly as T equal to k times theta. Okay. Now, how do we do equivalent nodal analysis for mechanical systems? In the electrical systems, we had direct laws, right? You have a circuit interconnected, then you write the relevant, identify the loops or identify the nodes, write down the voltage laws, write down the current laws, and you have sort of beautiful equations which describe for you the entire dynamics of the system. Okay, let us see the analogous of those kind of equations or those kind of conservation laws in mechanical domain. Okay, so we should first have our system structure that would suit the nodal analysis. And okay, let us see with the help of an example, right. So, I have a system composed of a spring, I have a mass element, I have another spring, and I have a damper or a dashboard, and this is my reference node, and with some external or with some force over here. The step 1 would be to identify the number of nodes, and these are identified usually by the number of displacements, right. So, I will have one corresponding to this guy here and the other corresponding to this guy here. So, these are my two nodes, right, node 1 and node 2, which will give me those two displacements. Okay. So, once I identify these two displacements or these two nodes, I just also identify these two nodes x1, x2, I mark them here, and then I have a reference node. Step 3, right, we just go back to how these guys were connected, that between node 1 and node 2, and then with between the reference I had the mass between node 2 and the reference, K2 between node 2 and the reference, B between the node 2 and the reference, between node 1 and node 2 I had the spring K, and the force was kind of acting on the node 1. Okay. So, we just draw some kind of a circuit diagram kind of thing over there. So, I have a force, x1, x2 are my two nodes. So, all these are the same, this is also x2, this is also x2, this is my reference node, so is this one, this guy is also a reference node. So, I have the force, I have a spring K1, the mass element, second spring, and the damping element, right. Okay. So, once I do these connections as stated or as in the previous picture, I have my something like a circuit diagram, right, and the force F acts on this node 1. Okay. Then I apply the Newton's laws at node 1, that I have a force and I have a spring. So, F would be K times the displacement, and since I am dealing with two displacements x1 and x2, I will simply have F is K1 x1 minus x2. Similarly, at the second node I say the sum of all the forces is 0, there is no external force coming from here, therefore, I will have the force corresponding to the inertia element as mx double dot. The force corresponding to K2 with displacement x2 would be K2 times x2, here would be B2 x2 dot, and K1 the displacement or the force corresponding to the spring K1 would be K1 x2 minus x1, and I have these two balance laws for node 1 and node 2, which will give me the overall mathematical model of the system, right. Okay. So, in summary, how do we identify the steps of a nodal analysis, how do we come about getting our models? The first is identify the number of nodes, which is equal to the number of displacements, select a reference nodes, and then connect all the basic elements, which are the mass elements or the spring elements and so on, according to their positions. Similarly, do for the spring and the damper. If there is an external source which generates or which produces a force or a torque, also add that to your system, and then finally apply the Newton's laws of motion to arrive at your desired equations. Okay. Now, if you go back and you see that there are these kind of equations look similar to what we had even for electrical systems, and we will then see, well, is there any analogy, because both systems are written a set of conservation laws, right. If I look at the electrical systems, I have the voltage conservation or the summation of currents equal to 0 in the Kirchhoff's current laws. Here I also have some kind of conservation laws, that summation of all forces is equal to 0. And based on these conservation laws, we will just try to investigate, is there a good analogy between these two systems, mechanical systems and electrical systems. Okay. So, let us investigate that one. So, that we could typically arrive at two kinds of analogies. One would be where you can say that the force or the input torque is equivalent to the voltage, where we have which we call the force voltage analogy or the FV analogy. Or we could also have situations where the force is analogous to current, or what we call as the Fi analogy. Okay, how to establish this? Okay, let us start with the circuit, right. So, again, based on the previous steps which were listed, I can easily write down that the force that this system which is exerted on this mass spring damper is mx double dot plus bx dot plus kx, which is a mass, a dissipative element, and a spring with a constant k. Similarly, for rotational motion, I can write down the equivalent of it. Okay. So, let us see, I have the equations for this guy, and see how do the equations on the right hand side look like. Based on KVL, we derived earlier also that L Q double dot plus R Q dot plus Q by C is the voltage that is applied. Okay, now these look very similar, right? So, I have a force as the input, here I have the voltage as the input, force produced a certain displacement, here voltage resulted in some charge and Q dot was the current and so on. Okay. So, therefore, I could say that force here is equivalent to the voltage, mass would in this case correspond to an inductive element, B the dashpot or the damper would correspond to a resistance, K the spring would correspond to a capacitor, and the basic system variable, the displacement, now corresponds to the charge. Okay. Let us go to the force current analogy. So, instead of having a voltage sourced circuit, now I have a current source circuit, which has elements in parallel, which I call as a parallel RLC circuit. This thing remains the same, F is mx double dot plus bx dot plus kx, and if I write down the equations for the circuit on the right hand side, what I see that based on KVL I get I is C phi double dot, phi is the flux, plus phi dot over R plus phi over L, the sum of all the three currents through the resistance, the inductance and the capacitor. Okay. There is some analogy. Now, force could be analogously seen as the current, the mass could correspond to the capacitor, B would be the conductance or the inverse of the resistance, the spring then would correspond to the inductance, like with the relation K goes to 1 over L, and finally, the basic system variable, the displacement here now corresponds to the flux here, and that is the reason we call it like the force to the current analogy. So, in my previous slide the mass element corresponded to an inductor, now it just corresponds to a capacitor and so on. Okay. To summarize, what we have done so far is to find or to establish an analog between the mechanical systems and the electrical system, the force to voltage analogy or the force to current analogy. Similar analogy would be even for the rotational domain, where I start from torque to the voltage or torque to the current, and this table summarizes the analogy between various elements, between the mass and the inductor or the mass and the capacitor or the basic system variable, which is the displacement x here or the displacement theta, to the charge or the flux. Okay. So, other kind of basic elements which we learn are systems which just transform energy from one system to other. In the electrical domain, we all know the transformer which transmits electrical energy from one circuit to the other through some electromagnetic induction properties. Analogously, in the mechanical domain we have gears, right, which is like again it just transforms mechanical energy from one mechanical system to other via gears. Here, well, I can say I can measure the transformer as either a step up or a step down transformer, which would change the voltage level. Here it could change the speed and the direction of motion, and they just look like this, right. So, if I have a transformer with turns ratio N1 to N2, V1 by V2 is N1 by N2, and the current would be the reverse of it, it will be I2 by I1, right. It will be a step up or step down based on if N1 is greater than N2 or N2 is greater than N1. Similarly, in the mechanical domain I have the torques on the both sides related by this relation, the torque T1 is related to T2 via the radius or inversely related to the angular velocity. So, these are again equivalent elements in the electrical domain to the transformer and to equivalently a gear in the mechanical domain. Okay. So, what have we learned so far? We have classified physical systems and specifically concentrated on mechanical and electrical systems and their basic elements. We saw how by using basic conservation laws via the nodal or the loop analysis helps us get the dynamics of the system. We also established a beautiful analogy between electrical and mechanical systems, and towards the end also learned about energy transformation devices like just the transformers and the gears. So, what we will do next is to also learn some more physical examples, right. So, starting from cruise control of a car, we also look at some more details of the transformer, of why what we saw in the previous slide is not really fit for analysis, the simple pendulum, and something which might be a little new, called the predator prey models, which I will explain you while we reach there.